Balancing exploration and exploitation. The dilemma of learning. A fundamental challenge in reinforcement learning is the trade-off between exploration and exploitation. To maximize its rewards, an agent needs to exploit its current knowledge by choosing actions that it believes will yield the highest payoff based on its past experience. However, if the agent solely focuses on exploitation, it risks getting stuck in a local optimum, never venturing out to discover potentially better strategies. This is where exploration comes in. By occasionally choosing actions that may seem suboptimal based on its current knowledge, the agent can explore new areas of the state space and potentially discover hidden rewards or more efficient ways to achieve its goals. Finding the right balance between exploration and exploitation is crucial for efficient learning. Various exploration strategies have been developed to address this dilemma. Some involve adding randomness to the agent's action selection, while others encourage the agent to visit less explored states. The choice of exploration strategy often depends on the specific problem and the characteristics of the environment. Section 4. From Theory to Practice. Implementing Reinforcement Learning. While the theoretical underpinnings of reinforcement learning are fascinating, the real excitement lies in seeing these algorithms come to life in practical applications. Fortunately, there are now numerous tools and libraries available that make it easier than ever to implement and experiment with reinforcement learning. One popular choice is OpenAI's GYM, which provides a collection of environments for testing and benchmarking reinforcement learning algorithms. From classic control tasks like balancing a pole on a cart, to Atari games and robotic simulations, GYM offers a diverse playground for exploring different learning paradigms. For building and training reinforcement learning agents, libraries like TensorFlow Agents and Stable Baselines 3 offer a rich set of tools and pre-implemented algorithms, allowing developers to focus on the specifics of their application rather than the intricacies of algorithm implementation. These tools have significantly lowered the barrier to entry for practitioners, enabling a wider audience to leverage the power of reinforcement learning. Section 1. Reinforcement Learning in Action. Transforming Industries. The theoretical foundations of reinforcement learning, while impressive, truly come alive when applied to real-world problems. This powerful approach to machine learning is no longer confined to research labs. It's actively reshaping industries, driving innovation across a multitude of sectors. From optimizing complex systems to personalizing user experiences, reinforcement learning is proving its mettle in tackling challenges that were once deemed too intricate for traditional algorithms. One of the key strengths of reinforcement learning lies in its ability to handle sequential decision-making in dynamic environments. This makes it particularly well suited for applications where the optimal course of action changes over time, based on feedback from the environment. Consider the energy grid, a complex network with fluctuating demands and supplies. Reinforcement learning algorithms can be deployed to optimize energy distribution, balancing supply and demand in real time, minimizing waste, and enhancing the stability of the entire grid. In the realm of healthcare, reinforcement learning is showing promise in personalizing treatment plans for patients with chronic diseases. By continuously learning from patient data and treatment outcomes, these algorithms can tailor treatment regimens to individual needs, improving patient care and outcomes. This ability to adapt and learn in dynamic environments makes reinforcement learning a game changer, ushering in a new era of data-driven decision-making across various domains. Section 2. Robotics and Control. Breathing life into machines. Robotics stands as a field ripe for revolution by reinforcement learning. Imagine robots that can learn intricate tasks, adapt to novel situations, and collaborate seamlessly with humans. This is the promise of reinforcement learning in action. By leveraging this powerful learning paradigm, we are moving away from robots rigidly programmed for specific tasks towards machines capable of learning and refining their skills through trial and error, much like humans do. One area where reinforcement learning is making significant strides is in robot manipulation. Tasks that were once considered too complex for robots to master, such as grasping delicate objects or assembling intricate parts, are now within reach. Reinforcement learning algorithms can train robots to perform these tasks with remarkable dexterity by rewarding successful attempts and penalizing failures. Beyond manipulation, reinforcement learning is also enabling robots to navigate complex environments autonomously. From warehouses to hospitals, robots are learning to map their surroundings, plan optimal paths, and avoid obstacles, all without explicit programming. This newfound autonomy is poised to transform industries, leading to increased efficiency, productivity, and safety in a wide range of applications. Section 3. Games and Virtual Worlds. Mastering complexity through play. The world of games has proven to be a fertile ground for advancements in reinforcement learning. Games, with their well-defined rules, scoring systems, and challenging environments, offer a perfect sandbox for testing and pushing the boundaries of AI. This synergy between reinforcement learning and games has led to some of the most impressive demonstrations of artificial intelligence in recent years. One notable example is AlphaGo, the AI system developed by DeepMind that defeated world champion Go player Lee Sedol in 2016. AlphaGo's success was a watershed moment for AI, showcasing the power of reinforcement learning in mastering a game of extraordinary complexity. Trained on millions of games and playing against itself countless times, AlphaGo developed superhuman proficiency in Go, a feat once thought to be decades away. Beyond board games, reinforcement learning is also making waves in video games. From mastering classic Atari games to competing at a professional level in esports titles like Dota 2 and StarCraft 2, AI agents trained using reinforcement learning are demonstrating remarkable abilities in complex, dynamic environments. These advancements in game-playing AI have far-reaching implications, pushing the boundaries of what's possible in areas like robotics, autonomous systems, and even scientific discovery. Section 4. Beyond Today. A Glimpse into the Future. As we stand at the cusp of a new era in artificial intelligence, reinforcement learning stands out as a beacon of progress, promising to reshape our world in profound ways. The advancements we've witnessed so far are but a glimpse into the transformative potential of this technology. From personalized medicine and self-driving cars to smart cities and advanced robotics, the applications of reinforcement learning are as vast as our imagination. However, this journey is not without its challenges. Reinforcement learning algorithms can be computationally expensive to train, often requiring vast amounts of data and processing power. Ensuring the safety and reliability of these systems in real-world scenarios is another crucial aspect that demands careful consideration. Despite these challenges, the future of reinforcement learning is brimming with possibilities. Researchers are actively developing new algorithms, exploring more efficient training methods, and working towards creating more robust and generalizable AI systems. As we delve deeper into the intricacies of learning from interaction, we are poised to unlock unprecedented capabilities, enabling machines to learn, adapt, and solve problems in ways that were once thought to be the exclusive domain of human intelligence. While the promise of reinforcement learning is undeniable, the path to realizing its full potential is not without its obstacles. Like explorers charting unknown territories, researchers and practitioners in reinforcement learning encounter unique challenges that require innovative solutions and a deep understanding of the underlying principles. These challenges, far from being insurmountable roadblocks, represent exciting frontiers for research and development, pushing the boundaries of what's possible in the realm of artificial intelligence. One of the primary challenges lies in the very nature of reinforcement learning itself, learning from trial and error. While this approach mirrors how humans and animals learn, it can be incredibly inefficient, especially in complex environments. Imagine a robot learning to navigate a cluttered room. It might take countless bumps and stumbles before it discovers a successful path to its goal. This inherent inefficiency poses a significant hurdle, particularly in applications where real-world data collection is expensive or time-consuming. Furthermore, reinforcement learning algorithms can be notoriously sensitive to the design of the reward function. A poorly designed reward function can lead to unintended consequences, with agents finding loopholes or exploiting quirks in the environment to maximize rewards without actually achieving the desired outcome. This highlights the critical need for careful consideration and design of reward functions that accurately reflect the true objectives of the task at hand.